Next on stage, we have Tim Ferkovic, NLP researcher at Belgrade, ready to illuminate us with his insights on multitask learning with intermediate continual learning for industry NLP use cases. Tim will present on using adapters and hypernetwork approaches for faster model training and efficient integration with ML systems. His insightful talk will focus on optimizing NLP solutions to meet the changing demands of different industries. Tim, welcome to the stage.
Hi. First of all, well, thank you for choosing to spend this 30 minutes here with me. What you can expect is, again, a bit more technical, research-oriented talk. I'll show some architectures, some numbers, what's the background of how this came to life. So basically, with multiple clients, they all have their own use cases that they want to fulfill. And it means that you shouldn't just have separate model for everything and then fine-tune it depending on the use case. So there was a need for something that can handle multiple tasks. Along with that, you, from your clients, often get requirements. Okay, now we want this new use case. Okay, now we're doing this use case, but we want new labels. Or you just have to have new data because there's been distribution shift. So there's also a need for some continual learning in all of this. So this MTL-CL framework is needed. That's why multitask learning with intermediate continual learning for NLP use case from the industry talk came to life. A few words about me. I'm an NLP researcher or engineer when needed at Belgrade and a recent data science graduate from FER in Zagreb. And what you can expect today is first we'll set some backgrounds of all of this, which will be familiar to. Then we'll go over the motivation. Why would somebody need this? I will cover the data. I think that's also the important part, to show what data I've been working with. Then the baselines, when we're using new methods, in this case adapters and hypernetworks, we need something to compare them to, like to see if it's actually better. Then the actual adapters and hypernetworks, the core of this talk. I'll show the results and conclude everything in the end. Right, so why? What's the setting and why would we need this? The setting is very familiar. 2017 attention is all you need. 2018 BERT. Well, in this work I've used BERT. You can use anything else. You can just change a few lines of code and use a different model. This is just like a proof of concept that this can also work. Also, it can work with non-discriminative models. You can use it. The approach can be used with generative models as well. So this is the proof of concept that it can be used in other settings as well. And well, now the normal procedure is, okay, you have a task, you fine-tune the task. You get another, but then we have 20 tasks, you fine-tune 20 different models, and it just becomes unbearable. That was the motivation. We want to use less storage than 20 different separate models and less VRAM possibly. We want to reduce the training time. We'd like to share some knowledge because often the use case that those clients have, or the one within the same client, are very, very similar. Maybe they have the same domain, maybe the legal documents, both of them, and sometimes you just feel like these models could benefit from sharing some knowledge or sharing some parameters. They shouldn't be just separate. And last, we'd like to use less computational power. Everything here is done with discriminative models, and on one GPU, Tesla T4 with 15 gigs of RAM, so it's very, very low computational effort. Right, I'd like to say something about the data, because on this slide you'll see, first of all, very low resource data. Don't worry, on the next slides there will be some actual data, and keep this in mind, because later when I come to results, the fact that these data sets were so low resource will have some implications on the results. And this is the classification data, and then we have named entity recognition data, 4 different data sets, like 4 different use cases, you would say in this case. And if you multiply the number of documents with average number of splits per document, you get the actual number of training examples. So this is higher again. As to the number of classes, again, it's higher. So the problem itself is more difficult. There's more classes, and we can assume that the model will more focus on this NER task compared to the classification one. Right, so when we have these 3 classification and 4 NER data sets, we need to simulate the actual environment. So we'd like to split the data sets into multitask learning part, which will be like the first stage, and we'd like to simulate this continual learning part, which will be the second stage. Continual learning will be done in 2 stages, like the first part of the data sets and the second part of the data sets to again simulate the real world environment when you have multiple incoming stages of continual learning. And there's 3 possible, most often cases in the literature. That's task, class, and data incremental learning. Well, clients come up with completely new use cases. It's a new task. They have the same use case, but they want, okay, we'd like these 2 new labels, and then you have class incremental learning, or just you face distribution shifts and you have to do data incremental learning. So the zeroth approach, besides of course, a single task learning, is the shared encoder. This is like the first thing that would come to mind, and it's simple. Basically, instead of n different encoders, you just share one encoder in blue. It's updated by all the tasks, and they then have task-specific heads. And the motivation is, of course, to reduce the number of parameters by n. We'd like to share some knowledge. Maybe the tasks are similar. They could benefit from each other. We'd like data efficiency, because if you have low resource task, that's the classification data sets that you've seen. Maybe they can benefit from the higher resource tasks, right? Because they don't have that much data that they can benefit from this. But then you have a lot of problems. How do you sample which task to choose at which point? How do you make up the batches? Are they going to be homogeneous, or are they going to be heterogeneous? How do you weight the losses? Maybe you have the classification loss, maybe you have the regression loss, completely different. How do you weight them? Maybe very different number of labels. And also, if the tasks aren't actually compatible, maybe they are a completely different domain, this is legal, this is medical data, then maybe you need to introduce the whole new step, which is like, okay, let's group the tasks that are compatible and then do this. So a lot of problems because we're sharing the parameters directly. Later we'll see how the hypernetwork does this in a much smarter way. Then we actually come up to the first approach that we're examining. So far we've split the data, we have our baselines that we're comparing with, and now let's see this approach. Adapters, they're small, they're modular, and the motivation is that we'll add some extra parameters. There will be very few of them, so like 0.5% of BERT parameters in total. The literature shows that the performance stays actually on par. We'll see if this also stays on par for our use cases, which is very specific. And they're modular. This is, I think, the beauty of the adapters. You can download those weights, plug them into your architecture, train them, save them, share them with somebody else. They can do the same thing. And even though the adapters themselves don't share the parameters, in this way, this is like distributed multitask learning. That's why I like to include the approach in the multitask learning as well. 2 architectures that I've examined, there's plenty of them. These 2 were compatible with other approaches, which I will later show. So on the left, it's just the, let's say, normal version of the adapter. You can recognize in gray, it's the transformer layer, and then pinkish color, just feed forward, down, and up projection matrices. There's nonlinearity, there's residual connection, but a simple architecture. And on the right, additionally, some mathematical tricks are used to further reduce the number of parameters. So these are like hypercomplex, parameterized matrices. So the weight matrix itself is split into 2 groups, like A and B, and then the sum of their chronicle products is done, and additionally one of them is low rank. So a lot of mathematical tricks just to further reduce the number of parameters, even though in this case this may not be that necessary, since already the number of parameters is pretty low. And then, so far, what we've done. So, for example, we had our 5 tasks, and we trained 5 different adapters. And now we have another incoming task, this continual learning task, and we can either train, okay, a new adapter or use the adapter fusion approach. So if this new task is very similar to the ones that we've already seen, we can utilize those adapters that have been trained and just train the adapter fusion of those adapters. The adapters themselves will stay the same. We're not training them, so they can be still used for the tasks that they're meant to be used for, but we're training this fusion of adapters, which is basically the attention mechanism. So we just see, okay, how much attention should we put on which of the adapters for each of the training examples. And by that, we actually weight the adapters and combine them for this new task. Right, so what we've done so far, we have our data, we have our baselines, and we've done the adapters approach. But there seems to be the discrepancy between the shared encoder approach, which shares almost all of the parameters directly, and the adapters approach, which are small, but they don't share anything. And this is where the hypernetworks fill the gap, because the hypernetwork is the network that generates parameters of another network, and that was exactly the motivation. So we want to do both. We want to share the knowledge via this hypernetwork, but we want to share it in a smart way, so that the task-specific components are also here because they're generated by this hypernetwork. And what I mean by this, you'll see now on this slide. We'll stay a minute or two here, so don't rush it. Again, component number 3 is the standard transformer layer that you can see. Component number 2 is the familiar adapter that I've shown previously. However, now component number 1 on the left is the hypernetwork, and this is where the magic happens. And we'll start from the bottom of the component number 1, from the task, language, and layer embeddings. First of all, task embedding. So all of these different, well, we have use cases of different data sets or different tasks. They have their own task embedding. Furthermore, maybe you have identical tasks which do the same thing. They may be even in the same domain, but they're of a different language. Then you don't have to change the task embedding. You could just change the language embedding, and you would actually benefit from the training of this same task on the different language, right? And lastly, we have a layer embedding, actually multiple, because you don't want to have a different hypernetwork in each of the layers, right? Since I'm here just for proof of concept, using the BERT base version, so you would have 12 different hypernetworks, which is unnecessary. You just have one hypernetwork and then 12 different layer embeddings. This reduces the number of parameters significantly. You probably wouldn't say, but each of these embeddings is just 64 elements. I've tried increasing it to 128 respectively, or to 256. It does not bring any benefits. It's even worse. So just 64 each, and this gets concatenated and given to the source projector network, which is just a fancy name for two matrices with nonlinearity again in between, and it has two purposes. First of all, it's okay to reduce the number of parameters. You can see that it goes from 6 dots to 2 dots. And then second is to actually learn how do these task, language, and layer embeddings interact with each other. Learn this interaction. Furthermore, we have another matrix, and then the parameter vector is spit out. And this parameter vector is always of the same number of parameters, then which gets reshaped always in the same way into this adapter. And now this adapter is used in the forward passes. So if the inference example is being used, it basically wouldn't know that there was a hypernetwork. It would just go through this transformer layer and then through the adapter. When we go back, everything is trained end-to-end, so the gradients are back-propagated through this adapter, and then the hypernetwork, and then all the way back to the embeddings, and they are also trained. While the gray part, the transformer layer is frozen. It's unchanged. Now the fun part is what are the results of this? You will now see quite a lot of numbers, but we'll slowly go through everything. What you see is the macro average F1 scores. On the left, you can see the data sets that I've talked about. So 10 in total. So we had classification and NER data sets, and then we split them as I said, into the multitask learning and continual learning part. Multitask learning is this upper half, while continual learning is this lower half. So you can have either C, T, or D, IL, which is class, task, or data incremental learning. Then on top, first row is the actual approach, the single task learning sharing encoder adapter, the fusion of those adapters, and the hypernetwork. For the hypernetwork, you can see two numbers, which is because we also want to compare, okay, how much did the performance of these tasks trained in the first stage, the multitask learning ones, drop after the 2 stages of continual learning, right? Because these 5 bottom half tasks of continual learning are not all trained together, but first 3 were given and then the remaining 2 to simulate like more of a real world case. Right. So we'll start with multitask learning, and we can see that with the average scores, the single task learning and the adapter and hypernetworks, we'll just taking a look at the left number for now, all perform very, very similarly. The hypernetwork lags behind by 1 performance point, but it's all similar. And while the sharing encoder is, well, the baseline is behind. But then when we go next to the continual learning part, again, the hypernetwork and the adapter data sets, we're taking a look at the last row, they perform similarly. Adapter fusion as well. Sharing encoder, again, lags behind. But the fun part is these hypernetwork, the 2 numbers. How did the previous knowledge that was trained during multitask learning, how do we still keep this knowledge? And yeah, that's the important part, and I forgot to mention is how is this knowledge preserved? Well, if we go back, I don't. If we take a look at the hypernetwork, I don't really care if during continual learning the parameters of the hypernetwork change. No, what I care about if the parameters of this generated adapter change, because this is the thing that's going to be used in the forward passes. So the regularization is done by comparing all of these previously generated adapters with the ones that would be new after the parameter update, and we want to penalize how much they've actually changed. So the L2 regularization is used for the generated adapters, not for the hypernetwork itself. That's how the CL is done. And now taking a look at the performance drop, we can see that the classification data sets performance drops significantly from 20 to 35 F1 score points, whereas the NER ones dropped slightly from 0.5% up to 2% after those 2 rounds of continual learning. And this is, at least for our use case, acceptable, because we had new requirements and we managed to train new upcoming tasks while also preserve almost all of the knowledge of the previously learned tasks. However, the classification data sets, and that's why I said that you should keep in mind that they're so low resource, they dropped in performance. You can generally see that they're not difficult because all of the classification data sets, they get classified by almost 1 macro average F1 score. But that's one thing that they're not difficult. Their loss curvature is probably not that deep. It's quite shallow, and besides that, they have little gradient updates. So probably you don't get that much into this loss that deep, and you can easily get out when you are later doing this continual learning. And that's why I believe that the performance dropped, because they're easy and they're so low resource compared to the NER. But also, a very important thing is how does this perform in terms of time and training parameters? Here the numbers shown are necessary for 5 tasks and only the multitask learning part, so not the continual learning part itself. The base is like the single task learning that we're comparing with. And we can see the adapters generally perform faster and use only less than 1% of the parameters compared to single task learning. Fusion is somewhat slower. This is because the examples have to go through all of the adapters and then get fused. And it's also slower during inference. So it's not the approach that we would go with. In terms of parameters, okay, it's less, but still not that few. Shared encoder seems to be like the fastest, and it has, of course, 1/5 of the parameters because it's one encoder instead of 5. But the asterisk is here because here it was used with mixed precision. All of the other things weren't, so there's, again, space for improvement, even though the single, not very sophisticated GPU was used for all of this. And Lightly hypernetwork, again, faster and less parameters, but not that good as the adapters, right? To continue, I also mentioned those two architectures of the adapters. How do they compare? Well, the first one that has a bit more parameters seems to be better in both the multitask learning and the continual learning part. The compactor does reduce the number of parameters, but it also hurts the performance, so it's not something that we would choose. And when it comes to fusion of those adapters, again, the fusion of the first configuration is faster than the fusion of this compactor configuration. Well, to conclude everything up, what are the takeaways of this? First of all, just taking a look at the multitask learning part so far, not taking continual learning into account. Both adapters and hypernetworks do seem to be much more efficient while preserving the performance same as the single task learning. Then when talking about the hypernetwork, it's different compared to adapters in the sense that it's a single model, so it does share some knowledge, whereas the adapters are completely separated. And that's why the results also in a single model. Whereas, as I said, adapters, they still require this separate deployment for each use case, as you had with single task learning. Of course, now deployment is much easier because it's only one, it's much less parameters, it's one adapter. But still you would have this separate model for each use case. And then talking about the continual learning part, well, first thing that has to be mentioned is this low resource problem, which, to be honest, you wouldn't have in the real world scenario. You wouldn't deploy these models to your clients that have so little training examples, but I'm glad that it was included because the problem can be seen when there is such a great discrepancy between the number of examples in one data set and in the other data set, and then you try to train them via multitask learning. And the other thing is that the training time does actually increase with the number of tasks in continual learning. Because you, as I said, you have to regularize for all these previous tasks. You have to reduce how much the generated adapters would change. And this is expensive. Every time you're updating parameters, you're saying, okay, let's see how much all these generated adapters actually changed, and let's penalize this. So yeah, but with that being said, I do believe that the approach is promisable. And I thank you for your attention and open the floor for any possible questions.
Here. Just start speaking. It will work.
Very much for your wonderful talk. I was wondering, like, when you told about hypernetworks, you mentioned that there is some embedding encoding, right, that you pass to your hypernetwork. And I was wondering, like, how it's represented. Like, it's like one-hot encoder vector, or it's also some embedding that we train. Is it aware of its position inside the network? Maybe you have some insights on that.
It's not one-hot encoding. So you initialize it completely randomly, just as you would do with the weights, but with probably normal distribution. And it gets trained end-to-end just like all the other parameters. It is, of course, aware of the positioning, which of these 64 parameters is at which position. And then everything else is left to the end-to-end backpropagation, which learns this positioning and sees. Because the task embedding is of course, only updated for when this task is sampled. Of course, it's not updated when some other task is being sampled and used. And in that way, it gets trained.
Okay, here.
Yeah, thank you for your talk. I just wondering, did you calculate what will be if you have like completely different single task neural network for each task? What the performance will be comparing to multitask?
Yeah, that's the single task learning performance that's shown here.
Oh, okay, so this one.
Yeah, so it's completely comparable. The adapters in hypernetworks compare basically the same as if you fine-tune the whole model and use so many more resources and so much more storage space.
All right, thanks.
Any more? Okay, yes.
Diversity of the tasks. Does the diversity of the tasks influence the performance of this approach?
Does the diversity of the task?
Influence the performance of this approach?
Yes, I think it's beneficial when the tasks are kind of similar, as with the sharing encoder. But here you have this benefit that you're not directly sharing the parameters, right? You're sharing the network that generates the parameters. So, okay, it can benefit from it because we have these task embeddings and they can learn the interactions. But again, you are mitigating this effect of negative impact when the tasks are completely different because, again, you're not sharing the parameters directly. I believe that the performance is the best when you are just using similar tasks. What we can see that with something that we should get more into it, but okay, with data incremental learning, maybe the performance of the hypernetwork seems to be slightly better than other approaches. You can see that NER-DIL dataset, that the performance of the hypernetwork is the best. Why? Because it's already seen this problem, but this is just additional classes, like data incremental learning, and then it benefits from this. Yeah.
Okay. If there are no more questions, Tin, thank you very much for this. This is a certificate for the lecturer. And thank you again. I mean, we can applaud to Tin.
Thank you.